안녕하세요. 자, 들리시죠? 그 9주차 숙제를 제가 이번 주 금요일까지 올렸는데, 잠깐만요. 한번 확인해 볼게요. 그러니까 5번째 숙제죠. 이거는 이번 주 금요일까지예요. 이번 주 금요일까지 하시면 되고, 다음 주는, 그러니까 이번 주는 그냥 수업이 있고, 다음 주는 수목금이 학부 입시랑 겹쳐서 계속 휴강을 할 거거든요. 다음 주 전체는 휴강이고, 다음 주, 그러니까 이번 주까지 9주차 숙제, 9주차 슬라이드에 있는 거 숙제하고, 다음 주는 휴강이니까 숙제 없고, 그 다음 주에 숙제를 또 내드릴게요. 보강 날짜는 아마 학기 직전에, 학기 종료하기 직전에 한번 잡을 것 같은데, 복습할 겸 뭐 오프라인으로 하든지 아니면 온라인으로 하든지 정해가지고 공지해 드릴게요. 잘 들리죠? 네. 자, 일단 시작해 봅시다. Okay, so last time we talked about the double integral and triple integral and how to compute those integrals using the Fluidic Theorem. And also we talked about the line integral and surface integral. So these are the main theme of the second half of our course. So let's review the important concepts again here. So double integral sorry, I have to change the screen here. Okay. So double integral is denoted by this symbol, and sometimes also denoted by f of dx dy, assuming that this d is a bounded region inside of xy plane. And when you have a continuous function on d, and d is represented by two equations, two inequalities, that x is bounded from a to b and y is bounded from g1 to g2 depending on x, then the Fluidic theorem says that we can compute this double integral using iterated integral as follows. So note that we have an opposite order of the dx and dy. Here we have dx and dy. We have dy dx here. So in iterated integral, the order is important. It gives you the order of integration according to the variable of x and y. So here we take the integral on y first and then x next. Here we don't think about the integration. So this is the definition of a value which represent a volume under the graph of function over the region D, or you can think about it as a limit of a Riemann sum. And the triple integral also similarly defined. We have integral is denoted by three integral signs, f and dv, or sometimes it's denoted by dx, dy, dz, assuming that v is a bounded region inside of xyz space. So the difference between double and triple is this function. In double integral, the integrand is two variable function defined on x and y. Here we have three variable function defined on x, y, z variables. And also, if you have an expression of the bounded region V in terms of three inequalities, first, x inside of this region is bounded from A to B, and next we have a y bounded from G1 to G2, and the last we have the limit, lower limit and upper limit of z depending on x and y. Then we can write this, you can compute this triple integral using three iterated integral, g1x, g2x, and h1xy, h2xy of f dz, dy, dx. Again, the order of this dx, dy, dz is important in the iterated integral because it gives you the order of integration. So you have to understand why this works intuitively. So always remember the picture of two-dimensional picture and three-dimensional picture. First of all, the two-dimensional picture of this Fluidic theorem is that you have a region bounded by two equations, G1 and G2. Suppose that this, so if you draw a vertical line which is perpendicular to x-axis and set two bounded, two left limit and right limit vertical lines which touches this region D. Then you have a line or a curve which bounds the region D on the lower side, and the other side, on the upper side, we have another line bounding the region D. So we have G1, here G2 and G1, whose graph is this bounding curve. So then the first Fluidic theorem says that we are taking an integration on each of x coordinates. So we are taking integration from here to here, right? And we are multiplying that with the, again, we are taking integration on x next. So we are taking the thin width, thin strip on the coordinate x inside of this region D, and then take the sum of these, sum of the area of the thin slices or thin strips of the region D. So then we get the entire area of D. So we take the multiplication with the value of function f. So depending on the meaning of the function, we are taking area and then multiply the function value and then adding all the sums. So you get the double integral. If you think about that, if you think about the function meaning that it's a density at the point, then this integration gives you the mass of the region D. Or if you think about as volume, which means that the area of this thin strip is the area under the graph of functions, and by multiplying the value of function or integrating the value of function here, we are taking the section area under the function, under the graph of function. So for example, let's say this is our z-axis. So the graph of function is hovering over this region D, and by taking this section, so I have somehow taking the section under the graph of function. Section at under the f of f, which is equals to g1, g2 integration of f dy. Okay, so and then we are multiplying that with dx, which is the thin width of this section, and then taking integration from a to b, from here to here, we get the volume under the function. And for the triple integral, you have to remember the similar picture, but now we can draw the graph of function in four-dimensional space. So you have to look at only the bounded region V inside of this three-dimensional space. So suppose that we have a bounded region V here. So by separating these expressions, first I take the lower the minimum value of x inside of this region and maximum value of x inside of the regions. So that's a and b. And then for each x, so which means that I'm taking a section perpendicular to x. So when I take the section at x, like so like this section, so I will get, so section of this v will look like, well, this kind of figure inside of, so this is section at x, okay, inside of a plane which is parallel to the YZ plane. So inside of that section, I have a lower limit and a minimum value of y coordinate and maximum value of y coordinate inside of this section. And for each coordinate of y, I also have a minimum value of z and maximum value of z. Okay. So I'm taking an integration in sequel. First, I take the integration over z-axis, so I get the integration over this set line segment. But when I take the integration, I take the value of function and then multiply that with this line segment. Okay, so I'm just not just taking not just multiplying the value with this length. I'm taking integration. So for each small line segment, I'm taking the value of function at that point and then integrating. So if you think about this function as the density at the point in three-dimensional space, when I take the integration over this line of this function, I get the mass of this line, okay, mass of this line. And then I take the integration over y, I get the mass of this section. And then if I get the integration over x at the end, then I get the mass of this volume, V, okay. So here's the two pictures that you have to always remember. If you have to be able to explain this Fluidic theorem without proving mathematically why this Fluidic theorem works. And we also define the line integral and surface integral. So when you define the line integral, you need a line, obviously. So when not just a line, but you also have you need a parameterization of a line. So let's say this is our A to B. So the parameterization, the domain of interval is, it can be anything, but usually we just take the 0 to 1, or depending on the situation, you can take another interval. So let's say we have a parameterization C which lies inside of two-dimensional plane. So I will write this Ct as xt, yt, where xt and yt are coordinate functions on x coordinate and y coordinate on this curve C. So when the function is defined on the line, this curve C, then we say the line integral denoted by integration f ds, where s is a small s, not capital S, is defined to be the integration from a to b of f composite CT, and then you take the multiplication of absolute value of, I mean not the absolute value, just the norm of the vector C prime t, using the same absolute value symbol, but it's a norm of the vector. This is a line integral. So this is the definition, not just the theorem. Okay, so unlike the Fubini theorem, this is just the definition. So you also have to remember why does this definition make sense. So when you're taking the line integral, the idea is the same. You have a line, you're going to chop your line into small pieces, and then for each pieces, you're going to multiply the value of function and then add them all. So think about your line inside of the two-dimensional plane. So it has a definite start point and end point. I'm going to chop this line in a small segment. And for each small segment, you can approximate your line with the straight line. Okay? So for example, so I can approximate this part into straight line, straight line, straight line, straight line, connecting the two endpoints. But if you enlarge one of the segments here, so I'm going to exaggerate a little bit, because if you make larger and larger sections here, larger and larger subdivisions here, curve will almost exactly same as the approximated the line, but I'm going to exaggerate. So this is our curve from here to here, the one segment of the curve. And here's the line that connecting the starting point and end point of the line segment. But what I'm going to do is trying to approximate this line, the segment of the line, with the line segment whose tangent line will almost eventually equal. Okay. So I'm going to approximate the length of this line segment with the length of this vector and multiplying with delta t. So when I'm having C, let's say CTI and CTI plus 1, where I is from 0 to n minus 1, where n is the number of subdivisions, it takes delta t time, or delta ti, which is ti plus 1 minus ti time, to take 1 point from CTI to get to CTI plus 1. So if I'm moving in the direction of C prime ti, it takes delta ti time to get from here to here. Okay, so the velocity of C prime could be quite large, but we are taking a small segment of time so that I get the small segment of this curve. So I need to multiply this delta t. So actual length will approximate it by the length of the vector C prime ti times this delta ti. So length of C of ti to ti plus 1 is approximated by C prime, absolute value, C prime ti times delta ti. Okay? So this is the small segment of line. I'm going to multiply to this length of small segment with any value of function on this line segment, and then add them all. So I'm going to replace this line, the length of line segment, with the length of the vector, this vector, and then add them all. So these are what we are doing here. So this delta t becomes dt, and we have a absolute value of this C prime t, which is the normal vectors here, and we have a multiplication of function and then add. So this is the idea. And again, although this is a definition, you have to be able to explain why this makes sense in the sense of integration. So whenever you take the integration, the main concept is that you chop up things into smaller pieces and then add them all. So similar for the surface integral, I'm going to erase this picture. You can define your surface integral using the double integral. So again, you need a parameterization of surface. So I'm going to take that as x, which takes d to surface S. So d is a two-dimensional region, and S is a surface in three-dimensional space. Okay, so in principle, you have x uv is equals to x uv, y uv, and z uv. Okay. So you need three coordinates to identify the points inside of three-dimensional space. But for each coordinate is depending on only two variables because this is two-dimensional surface. So you only need two variables to define, to fully understand what coordinates are. So here are x, y, z coordinate functions. So surface integral is denoted by two integral sign and s of f. The s here, s is a capital S instead of small s in the line integral. And also this function is three variable function because we need to define a function over the surface S which lies in the three-dimensional space. So in principle, having two variable function defined on the three-dimensional space is impossible. So this function is a three variable function. How it defined is translate into double integral. So you're going to take the integral over the d, where d is the domain of the function, the parameterization x, and we take the composition of x and f, and then you multiply a weird component. It's called xu and xv. So we're taking x as if it's the value is a vector. So I'm taking a partial integral on each function coordinate functions, and I get the three-dimensional vectors and three-dimensional vectors again, and I take the cross product of that. And I get the norm of that cross product and multiply with the function. So and then du dv. So this is how it defined, and I explained why we need this term. The key idea is that when I'm taking the integration over d, the small segment of the region of d corresponds to small segment on the surface S in this three-dimensional space, but there's the difference between two areas. So the ratio between two areas of d and S are different, and this gives you the ratio. So this is the ratio between this small subregion in D and area of small subregion between area and the area of the corresponding subregion in S. Okay? So you have to multiply this term. So I also again explained why this term works for that ratio. So this is the summary of what we learned in the last week, but that's the really important part, or maybe the key parts of the second half or after the midterms of what we are going to learn. So if you have any questions, please ask now, or we're going to keep moving on this week 10. Okay, so let's look at slide again. All right, so this is week 10, where we're going to study also one of the most important theorem in double integral. All right, so what we are going to do is substitute variables in double or in triple integrals. Sometimes, in order to compute the double or triple integral, you need a Fluidic theorem, but Fluidic theorem doesn't work in many cases. So, in order to make the computation easy, you have to substitute or transform your variables. And here's the setup. So here we have D and R, which is two regions in the same dimensional space, Rn. So here I just took the n as a natural number, but you can think of n as 2 or 3 in our course. But usually it works for any dimension n, but think about n as 2 or 3. So a differentiable one-to-one function t from R to D is called the transformation. Okay, so what's the condition? So a map should be differentiable and also one-to-one, okay? So I'm going to talk more about one-to-oneness of the function. So also when you have a parameterization of surface and line, I said that it's okay to be not one-to-one at the place where the area becomes 0 or volume becomes 0. Okay, so here's the similar. So you don't have to keep the one-to-oneness strictly as long as the set of points where the one-to-oneness fails has the 0 area or 0 volume. Okay, so I'm going to talk about that later again. So so there's a typo here, u1 to un becomes x1 to xn. The Jacobian of t is defined as the determinant of differential of t. So think about the differential. I said the differential is always a matrix. So here we have a region in Rn, R, and also region D as a region in Rn. So we have two domain and range space have the same dimension. So differential is the square matrix, which is n by n matrix, so you can compute the determinant. You can define the determinant only when the matrix is square matrix. So we are going to denote this JT, which is called the Jacobian, as so this is how it defines determinant of the differential, but we are going to denote that as this way. So we are having the variables on the range space on the numerator, and on the denominator we have variables on the domain space, u1 to un. So this is a typo. I'm going to fix it. So this notation is very useful. I'm going to tell you right now. So here is the integration of substitution, integration by substitution. So let's say we have t from D to R, which is a transformation. I have to change this to opposite direction too. Okay, so it doesn't matter as long as it's a one-to-one. So let's say we have transformation from D to R, and we have a function defined on D. So it's function defined on the domain of the transformation. So we have given a integration over D. Okay. Then this integration is equal to the integration over R. Now the R is in the so yeah, D is in the XY. Okay. Sorry, that's also typo here. So this has to be R and this has to be U. So this is a typo. I'm going to write that in the blackboard again. So this should be R, and this should be D. So don't think about this the symbol in the bottom of the integration sign yet. So think about, I'm going to take an integration on xy plane, okay? So this r is in the xy plane. I'm going to take back to the region inside of the uv plane, and in order to pull back the region, I need to first substitute the xy coordinate into uv expression. So I have to composite this function f and the transformation t, and also I have to multiply this jt term, because when I transform this region from xy plane and uv into the uv plane, the area, the ratio of the area of corresponding regions are not equals to 1. So you have to accommodate that ratio. That's the term JT. So think about this. So this is a formula. You have to remember it, or you have to understand why it is derived. I'm going to explain shortly. But when you memorize this formula, it's very easy to confuse where this d or r come from, how to put your variables. So you have to memorize this way. So this is also r and d, okay? So don't think about this yet. So think about just the dx dy or du dv terms. So I said that my Jacobian can be written as this kind of ratio expression. So when I write my Jacobian as del xy in the numerator and del uv in the denominator, it's think about as if it's the du dv in the denominator. So I can cancel out with the du dv on the end of this integration symbol. So then what I get is dx dy. So I get dx dy. And f uv is originally just x and y, so I get the same thing here. So don't think about the integration sign or the symbol under the integration sign. Just think about the integrand, what comes into the integration sign. I just want to change my dx dy into du dv. Then I have to multiply this kind of ratio in order to cancel out so that I get the same thing. And also another important or useful thing is that when you represent your Jacobian into this ratio symbol, you can also think about the inverse of transformation and Jacobian of that inverse. So Jacobian of inverse of t is denoted by del uv over del x. This is also type of xy, okay? And that's equal to 1 over the Jacobian of t. So think about this as if it's a del y del x in the single variable function case. So you can switch that del y del x so that it's that's differential of the inverse function. So it's similar. So we have Jacobian of inverse, which is reciprocal of the Jacobian of the original function. Okay, so this is very useful notation. So we will see that why it's useful in this example. But first, let me write that out again. Integration by substitution. And let me explain why that works. So meanwhile, if you have any question, please ask anytime. If you don't understand now, you will not understand later. So just ask any questions. Okay. So here's the transformation t. Here, let's say our d here, and let's say our r. This looks like this. Okay. So this is our coordinate x and y. This is our coordinate uv. So function is defined on this xy plane. So f is a function, real values function defined on xy plane. So originally I need to integrate, I want to integrate over r, okay, just in using the term x and y. But you see the r is kind of weird figured region, so it's not easy to apply the Fluidic theorem or just using the definition of the double integral. So I have to transform my r into the well-shaped region inside of uv using the one-to-one function t. So then how it's done is, first, when I take f, I'm taking each coordinate x and y. So each coordinate x and y in the region R has unique correspondence inside of UV plane inside of D. So you have UV uniquely corresponds to a point xy. So taking a composition it's nothing. It's just obvious. You have to multiply the same value of function at the same point. So instead of taking xy as a identification of this point, I'm taking uv in order to identify the same point. But this term is not obvious. But anyway, this is the formula. So in the slide, there's a big mistake here. So this is r and this is d. I'm going to fix it. Now, why we are taking this ratio? So let me just first write y and then explain more detail. So this is the ratio between the areas in small subregion in UV plane and the corresponding also small subregion in XY plane. So here's a little bit of more detail. So when you try to do the integration, you're going to subdivide your domain, subdivide your region, right? So when I subdivide R, suppose that I'm taking subdivision of D into vertical lines and horizontal lines, and then the corresponding regions are following. So the lines, the straight line doesn't go to the straight line in R, okay? May not be going into the straight line R. However, I can make a larger and larger subdivisions so that if I take the small region inside of D, which is the rectangle, it becomes a small region in R, which can be almost looks like a parallelogram, okay? Not exactly the rectangles, but it's a parallelogram, because if you enlarge these red subregions, here's the picture. I'm going to draw it bigger. So we have UI, VI at this point, and here we have UI plus 1 and VI, J, let me say J here. Vj plus 1 here, and let's say this is our subregion in R. So this is xi, yj, and let's say this is xi plus 1, yj plus 1. So whenever I write my xi or yj, this is nothing but just a coordinate of this transformation t at yi and vj, okay? Now, I exaggerated a little bit here because if I enlarge or make it subdivision smaller and smaller, this region almost looks like parallelogram. So this is not a surface, okay? So this is just the two-dimensional region. I just draw this as some bounded by a curved line. Anyway, so if I have two vectors moving along the u-axis and v-axis, I have corresponding vectors here. And so let's say I'm taking a unit vector along the x or u-axis and unit vector along the v-axis. The corresponding vector here is tu and tv at the point xi and yj. Okay. And again, I'm going to approximate this area of these two areas. It's not enough to take the unit vector because this is a small segment, small line segment. Unit vector has a length 1, so it could be really large here. So I just made it small here, but I have to multiply the length of this line segment by taking the distance, taking the increment of ui to ui plus 1. So in fact, I had to, in order to take the vector which has the same size of this one length of the rectangle, this is delta ui 0, and here we have 0 delta vj, right? So here delta ui is ui plus 1 minus ui, and delta vj is vj plus 1 minus vj. Okay, the similar, same notation as before. So for these vectors, we also need to multiply the same increment of u and v in order to approximate the length of vector into the length of this one side of the bounded region here. So when I do that, let's say this blue one is tu delta ui, and here we have tv delta vj here. So again, I'm exaggerating the picture. So original area, the area of this region, original area of this region is not a parallelogram, but when I approximate that with, the parallelogram bounded by these two vectors, I get this area. Okay, so here the blue one and the white one. So the area of T of this region, ui plus 1 cross vj plus 1, is approximated by the area of parallelogram, parallel. Is it L? Is it, whether it is two L's in the front or in the second? Parallelogram bounded by these two vectors, tu delta ui and tv delta vj. If you take the small subdivisions, always, okay, I'm assuming that there we have a small subdivisions. All right, so what we're going to do is, what we are doing is take the area of these small subregions and then multiply the value of function at the point inside of the subregions. Okay, so instead of taking area of the actual subregions, I'm taking area of this parallelogram which approximate the subregion. So can I write here? Okay, so let me. Here I have to. So okay, so here R of f dx dy. How should I do this? So it's same as limit of sum. So I'm not going to write exactly what comes into the limit sign and sum signs. I'm just taking limit and sum in order to just show you the idea of the integration of f at xi star yj star of delta rij. So this delta rij is the area of this white region, the actual subregions, the subregion of R. And then, so instead of taking xi star and yj star, because t, the transformation is 1-to-1, I have exactly one corresponding ui star and vj star to xi star and yj star. So I'm going to take t of ui star and vj star instead of xij. So, and then the area of delta rij can be replaced with the area of this parallelogram, right? So if I'm going to multiply, this is not the dot product, just the multiplication. Area of parallelogram bounded by tu delta ui and tv delta vi. Okay. So let's compute the area of this parallelogram. How do you compute that? So these two vectors are two-dimensional vectors. You have to remember that these are two-dimensional vectors. The two-dimensional vector, the parallelogram, the area of the parallelogram in two-dimensional vector can be think of as the size of the norm of the cross product of these two-dimensional vectors considered as the three-dimensional vectors inside of xy plane. So which means that I have these two vectors, tu delta ui and tv delta vi. Think about these two vectors are lying inside of xy plane whose z coordinates are 0. So I'm going to take this as if it's a three-dimensional vector. First, so we have tv is equals to xv and yv, and tu equals to xu and yu. So here we have xv, yv 0 times delta vi, and this guy is xu, yu, comma 0 delta u. This is j, sorry, j. This is I, ui. Okay. And then take the cross product. So when I take that cross product, ijk, xv, yv 0, xu, yu 0, and then multiplying this. Actually, I have to take the tu first. Sorry, tu tv. So xv, yv here. Tu, yu, xu, xv, yv, and delta ui, delta vj. So this is a cross product, and I'm going to take the absolute value or take the norm of that vector. So what I get is inside of this absolute value sign, the I coordinates or the I direction, which is the x direction, becomes 0 because when I take the I, everything goes to 0 because of 0, 0 here. And also same for j, we have 0, 0 on one column, so all the coordinates of j become 0. So only the coordinate of k direction survives, which is this term. So the norm of this vector is same as the length of k coordinate, or the absolute value of the coordinate of the k direction. So this is xu, yu, xv, yv, and then del ui, del vj. Okay. So, and then, and then take the absolute value again, right? So I have to replace that here. But look at what I have here. What is this? This symbol is the determinant of 3 by 3 matrix, and also this symbol is determinant of 2 by 2 matrix. Okay. The determinant of 2 by 2 matrix of this form is same as determinant of the differential of T transformation, which is the Jacobian, right? So this is a Jacobian of T, and we have du dv. So this becomes limit sum f composite T of ui star vj star times. Now, when I multiply these, I need area. Okay, I don't need the sign. I don't need the plus minus sign of the vector. So I just take the absolute value sign at the around this vector. So I take the absolute value sign of Jacobian of T. So inside here, this symbol is not an absolute value sign. This is symbol for the determinant, which becomes a jt, and we have the integrate absolute value sign around jt. And we have del u, I, del v, j. So assuming that my ui and vj are increasing subsequence of the interval, so I don't need to put the absolute value sign around this delta. What do I get here? So jt is a function of uv. So here I didn't mention that, but jt is computed as at let's say here ui and vj at this point. Okay, and also I can replace this ui and vj as ui star and vj star as just ui and vj, which is the left bottom corner of this region. Okay, so it doesn't matter. I can choose any point inside of this region, including the boundary. So I just took the one corner point of this region. So then, what do I get? I have an integrand, which is f composite t times the Jacobian, absolute value of Jacobian of t. And around here, we have du dv term here, and we have a limit and sum, but sum means that I'm taking all the subdivisions, and limit means that I'm taking a infinitely many number of subdivisions for each coordinate. So it works for x and xy coordinate, xy plane, and also for uv plane. So if I take the subdivisions of xy plane, I also take the subdivision in uv plane. And if I take the number of subdivision goes to infinite, then also number of subdivision in uv plane goes to infinite. So you don't have to worry about this part. It only makes this sum becomes integration over d, because now we are lying inside of the space of uv plane. So we are taking integration over d of f composite t. Sorry, I have to erase this. uv times absolute value times du dv. So don't forget that you have to take the absolute value of jt. JT is just a determinant. It can be negative or positive. You always take the positive part, positive number of the Jacobian. Okay? So this is how you derive your integration by substitution. Applying this formula is easy part. You have to understand why this works. So even though we are going very slow, I'm going to explain more detail on the next slide. If you have any question, please ask any time. So here's a not so easy example, but we are going to introduce one more transformation before we do this example. But first, let's look at the integration without knowing that the integration by substitution. The way we have to do is trying to express my region D, which is the area of the unit circle, into two equations in x coordinate or y coordinates, and then and then compute this by Fluidic Theorem. I think it's hopeless if you try to do that using Fluidic Theorem. That's hopeless. But using the integration by substitution, it becomes really easy, and I'm going to introduce very useful transformation that can be used for many integration by substitution. So before I erase this part, is there any questions? Okay. So, in general, the integrations by substitution is in order to successfully apply your integration by substitution, you have to choose your transformation wisely. But many times, this transformation works. Let's say we have t inside of R2, and R2 defined by R theta becomes R cosine theta, R sine theta. I think you already know that. This is the polar coordinates of xy plane, right? So this is my x coordinate depending on r and theta, and this is my y coordinate depending on r and theta. So this is a very useful polar coordinates transformation. Let's say polar transformation. So let's try to compute our Jacobian first. So JT. Here, this is x, y, and this is r theta. So always the numerator must be the coordinate of the target domain, and the denominator must be the variables coordinates of the domain. Okay, and this is the determinant of. So this is the function that you have to take a derivative, and the numerator, the variables in the denominator is the variable that you take the partial derivative with. Okay. So xr and yr. So xr. Let's say, is that right? It doesn't matter actually. So x doesn't matter, but let's say we are taking how I did the term, how I used the Jacobian. So when I use the Jacobian, I take the determinant of differential, so this must be x zeta and y r and y zeta, right? Now, you may ask one question, okay? So this is the this part is the differential of t, right? This is the differential. But think about how we derived our formula of integration by parts. So we compute the area of parallelogram by taking this determinant. But here we have xu, yu instead of xu, xv. And here we have xv, yv instead of yu, yv. But if you take the definition of differential of this transformation, it should be this order. They are different. They are different. They have different rule. Is it okay to take? Sometimes you have x on the same row, but sometimes had x on the same column? So the answer is yes, you can take both definition, because so when you take this kind of definition of Jacobian, what you're doing is you're taking determinant of transposition and transpose of this square matrix. This is same as xr, x zeta, x yr, y zeta. So this is the transpose of differential of the transformation. So remark is that for any n by n matrix, let's say D, we have determinant of D always equals to determinant of transpose of the matrix. So you can either compute your Jacobian using the determinant of differential, or you can just simply take the transpose, saying that I'm going to choose the same variables on the denominator on the same row, so that I get the transpose of our differentials. Or you can just use the differential of the transform t in order to get the Jacobian. Doesn't matter. It's only for the Jacobian. So differential is this one, not this one. But when you take the Jacobian, it's okay. So let's try to compute using this definition here. So it's a determinant of, first you take the partial derivative of r cosine theta in terms of r. We have cosine theta. And you take the partial derivative of theta minus r sine theta. And y you have sine theta, and we have r cosine theta. So it's r cosine square theta plus r sine square theta. So this is r. So think about the transformation. So r and theta can be any number, but usually we take r as a positive number, and theta can be anything. But in order to have a one-to-one transformation, you cannot take any r and any theta inside of domain. For example, let's say we have xy plane here, and transformation, polar transformation, and here we have r theta here. So let's say we have r1 and r1 here, and we have 2 pi and we have 4 pi here. So these 2 points are going into the same point, which is, or this point. These all 3 points are actually infinitely many points going all to 1, 0, right? So if you take the entire r and theta, you don't get the one-to-one correspondence. So in order to have a one-to-one correspondence, you have to fix your range of theta to be the length of 2 pi. So usually we take from 0 to 2 pi. Sometimes we take minus pi to pi, doesn't matter. But let me choose 0 to 2 pi. And okay, so here in this strip, from 0 line to 2 pi line. And again, if you take the negative r, what happens? So let's say we have this point, which is 1, 2 pi in r theta plane. And how about we take, we have a -1 here, and take a -1, pi here. So these 2 points are mapped into the same point, because we take the -1 into r and pi into theta, you also get the 1, 0. So if you include all the negative side of this strip, you don't get the negative one-to-one correspondence either. So you're not going to take the negative side. So what we get is, in order to get the one-to-one correspondence, you only need to take r theta from this half strip. Okay? And then here's the one question. So if I take r from 0, bigger than 0, and also theta from 0 to 2 pi, does t gives the one-to-one correspondence? Doesn't give you one-to-one correspondence, obviously, because when you have a 2 pi theta is 2 pi, it always match with the theta equals to 0. So these two boundaries are mapped into one single line, which is these two line goes to these line. So any 2 points with the same r maps into 1 point. So this is not one-to-one. So you have to omit one of these 2 sides. And again, there's one more problem. So when r is 0, no matter what your theta is, it all goes to the origin. Okay? So one-to-one also fails at this line. So however, are we going to always think about our domain to be less than or equal to some numbers in order to take the integration by substitution? Or we just ignore what happens on the boundaries when you set the region? So we are not going to, the answer is we're not going to worry about what happens on the boundary, because what? At the boundary, in the corresponding xy plane, it has no area. Okay? So this line all goes to this point, and this line all goes to a straight line, which has no area. So when we are taking a double integral over some area, these areas with 0 area, this set which has the 0 area, doesn't affect the value of integration. So we are not going to worry about what happens on the boundary, so we will always put these equal symbols here in the inequalities. So let me write that out. So remark is that although one-to-one fails at the boundaries, we will not omit the boundary because the corresponding set has zero area. Okay? So let's try to compute that example. So here we have area inside of unit circle, and our antiderivative, integrand is absolute value x e to the negative x squared y squared dx dy. Okay? So we are inside of xy plane. Okay? And our integration region is the unit circle. So I'm going to pull back my range, pull back my region to the better region to integrate. So we have xy here. When I using the polar coordinates, my r is from 0 to 1, and my zeta is from 0 to 2 pi. So entire area, entire points inside of this unit circle is mapped into this square or rectangular region inside of r zeta plane. Again, this in principle is not a one-to-one correspondence because at 0 it fails, the one-to-oneness fails, and also on the upper and bottom strip we also have we fails the one-to-oneness of the transformation. But what happens is it maps to the zero area region, so we don't care about that. And let's try to use the integration by substitution. And then I'm going to integrate over r zeta plane. So r is from 0 to 1, and zeta is from 0 to 2 pi, and x becomes r cosine zeta, r cosine zeta, and we also have a straight absolute value sign, and becomes e to the negative of x squared plus y squared is r squared. And then what? We have dx dy. We need to change it to d zeta dr, right? So I'm using the order that I used in the integration here. What comes into the integrand is the Jacobian. So we compute the Jacobian again. So in here, wait, can I compute this? Let me try to do this. Okay, anyway. So we have r as a Jacobian, and then take the absolute value sign here. So that's that's what I have to integrate. First of all, it's easy to compute the integration over theta because r is considered as constant over theta. So we only take an integration of absolute value sign of cosine theta from 0 to 2 pi. That's 4. Okay, so we have 4 times 0, 1. And then we have square root, absolute value r twice. We have r squared and e to the minus r squared dr. And just a matter of this single integration. So I hope I can integrate that using integration by parts. So first of all, let's say So I'm going to separate out r and r times e to the negative r square dr. So then I have minus 1 over 2 e to the minus r square. That's the integration of this r e to the negative r square, and times r 0, 1. Wait, it doesn't make sense here. Let me give me a few minutes here. So right. Anyway, actually, it doesn't make sense. I mean, it makes sense, but we cannot find our integration by hand. So what happens is I'm using integration by parts, taking the integration on this side, and then I get minus of 0, 1, minus 1 over 2, and then e to the negative r square, and then take a derivative of r, which becomes 1, right? So dr, okay? Well, so here we have minus 1 over e to the minus 1. When r is 0, it becomes 0. And plus 1 over 2, 0, 1, e to the negative r dr. It has a value, but this doesn't have a symbol to represent this value. So usually it's called the ERF, well, anyway, but it has an absolute value. It's a definite value. So e to the negative r square in terms of r-axis looks like when r goes to infinite, it becomes 0. So it's 1, but it looks like this. So basically, I'm taking an integration from 0 to 1, and the area under this curve is the integration. So this is a 0, 1 e to the negative r squared dr. Okay. So anyway, that's how we compute this integration. If you try to do this by hand, I think it's getting worse. Let's look at the simple ones. Let's see. I want to take x squared y squared minus less than 1 e to the minus x squared plus y squared dx dy. Instead of having square root absolute value x, I'm just having e to the negative x squared plus y squared. But then I have 0, 1, 0, 2 pi of e to the minus r squared. I'm going to use the same polar transformation, dr theta. And then this becomes r dr d theta. And well, there's no theta, so we have 2 pi. And we are getting the 1, 0 r e minus r squared dr. So this becomes minus 1 over 2 e to the minus r squared from 0, 1. So we get pi of 1 minus e to the minus 1, right? So normally if you try to compute using Fluidic theorem, you cannot do this. You cannot find actual value by hand. But using the integration by substitution, you can easily compute that. And also, let's go back to the week 9 that we had in the example. Let me show you this one. So here, which one was it? Here, yeah. Let's look at this example. So in the class, we try to draw the region V and try to use the Fubini theorem 3. If you use the integration by substitution, this can be done really easy. So far we had the integration by substitution in terms of 2 variables. We can do this the same way in 3 variable case in triple integral. Do I have? Yeah, we have here. So integration by substitution in 3. Okay, also typo here. So anyway, so we have in the 3-dimensional space. Let's say we have V and W be regions, and let's say we have T, which is differentiable one-to-one map, which is called a transformation. Now again, this V and W is 3-dimensional region. So we need a 3 variable to identify the coordinates of the point inside of V. So we have a triple integral here. I omit this one more integral sign here. But the V is correct. So when I try to compute the triple integral over the region V, I can pull back my region to the W, which is the domain of transformation. And I'm trying to compute this function. So this part, the F composite T, is nothing but just F, because I'm just using UVW in order to identify X, Y, Z. But I need to also compute, multiply the absolute value of the Jacobian of T. So the role of the Jacobian, absolute value of Jacobian, is same as the role of the Jacobian in the 2-dimensional case. It modifies the ratio between the small subregions inside of XYZ plane and UVW plane. Sorry, the space. So before I explain the more detail, let me just let's look at the problem here. So think about this theorem again. Go back to the week 9. How we can solve this problem using integration by substitution. Let me erase this first and then switch the screen. Okay. So let's try to write our 6 boundaries in this way. So 2x minus y is equals to 0, and 2x minus y equals to 2, and y equals to 0, and y equals to 4, and z equals to 0, and z equals to 3. So I'm going to define my transformation UVW so in this way. So let me write this way. So I'm going to substitute 2x minus y into u, and v as y, and w as z. Okay. So then my boundary, my region bounded by 6 boundaries, is simply written as y equals to, u equals to 0, u equals to 2, and v equals to 0, v equals to 4, and w equals to 0, and w equals to 3, which are all the plane, just the plane perpendicular each axis. Now, so our objective is to transform my region V into the region W, which lies inside of UVW space. X, Y, Z. I don't remember how I draw this, but I think it was something like weird figure like this one. Remember? But anyway, but if I take that as UVW space, then here it becomes very nice space, squared space, okay? But here's the very important fact. So it's easy to substitute in this way. So you have to substitute the expression in terms of x, y, z into one symbol here. But when you write your t, so t is a function from u, v, w to x, y, z, okay? But your expression is not in terms of x, y, z expressed in u, v, w, but instead u, v, w is expressed in x, y, z, okay? So this expression is actually the expression for the inverse function of t. X, y, z is equals to u, v, w, where u is 2x minus y, and y and z, okay? So by substituting the expression of x, y, z, you're taking the coordinate functions of, you're finding the coordinate function of inverse transformation, okay? So let's try to compute the inverse Jacobian of inverse transformation. So remember how we expressed our Jacobian in terms of ratio. So this is del u, v, w, del x, y, z, okay? I don't put the absolute value sign yet. Jacobian is just this. When you take Jacobian into the integration by substitution, then you get take the absolute value sign. So this is determinant of what? First, you take ux, uy, uz, and vx, vy, vz, and then wx, wy, wz. And the determinant, so each elements are, so this is u, 2x minus y, 2, and y is minus 1, no z, and 0, 1, 0, and here 0, 0, 1. So it's very easy matrix, 3 by 3 matrix, whose determinant is just 2, because this diagonal part only survives. So this is 2. Now, this is the Jacobian of inverse. What's the Jacobian of t? It's a reciprocal of the Jacobian of inverse of t. Why? Because this is not a rigorous mathematical argument, but you can use it without worry. Because when I write this dt, I have to find the dxyz over duvw. That's a reciprocal of what we have in here, okay? So therefore, it's 1 over 2, okay? So I want to find that expression 2x minus y plus z over 3 dx dy dz. But I can transform that into integration over w. This is our w, okay, by the way. And this is our v, whatever that is. And I have to translate this expression in xyz into expression in yz uvw, but I already did that. So this is u over 2, and z is w, w over 3. Okay. And then before I change into du, dv, dw, I need to multiply the Jacobian, the absolute value of Jacobian. Jt, that's 1 over 2. So don't apply 2. We have to apply 1 over 2. And du, dv, dw. From now, it's just a matter of Fubini's theorem. So u is from 0 to 2. And v is from 0 to 4. And w is from 0 to 3. And that's u over 4 and w over 6 of the w, the v, and du. And you can easily compute that afterwards. Okay, so you have to remember that you have to multiply 1 over 2. Okay, so this is standard technique, easy example, but it's a very standard technique to using the integration by substitution. So everything, any integration will probably given in terms of the variable that you're already familiar with, the x, y, z. You want to replace that with another symbols, u, v, w, so for example, then you have to multiply the jt, which is the reciprocal of the jt of inverse, and that's because and the jt of inverse can be easily computed. Here we have a luck that we have no expression in terms of x, y, z. If it does comes with the expression in terms of x, y, z, then you also have to replace your x, y, z using in terms of u, v, w. But here we don't have that. So just take the multiplication of 1 over 2. Let's look at more complicated example. So here we have a volume of a region bounded by 2 cylinders. So one cylinder is along the z-axis, and the other, I'm sorry, so I should change this. So one cylinder is along the z-axis, and the other is along the x-axis. So this peak figure is representing the region bounded by these 2 regions. So think about a cylinder which is perpendicular, which is parallel to the z-axis, and then trying to slice that cylinder with the cylinder parallel to the x-axis. That's how we get this picture. I want to find the volume inside that. How can I find that? So I'm going to introduce some useful, another transformation in 3-dimensional space, which is called the cylindrical coordinates, as follows. I'm going to erase this. So T defined on 3-dimensional space to 3-dimensional space as r theta z goes to r cosine theta, r sine theta z is called the cylindrical transformation. So let's try to compute the Jacobian first. So the determinant of, first take the x here, so r, and then take the partial derivative in terms of r theta z in order. So we have cosine theta minus r sine theta, 0 because there's no z here, and sine theta r cosine theta and 0, and the last one is 0, 0, 1. So when you take the determinant, because of the 0, 0 here, only terms that survives is the cosine r cosine and sine minus r sine. So we get r cosine square minus and plus r sine square. So this is just r. Okay. So in order to find the volume inside that region, I need to take 1 as my value of function. It's a constant 1 function, and take the dx, dy, dz. That becomes the volume, right? Using the integration by substitution, I'm going to take back that region into the W, which lies inside of r theta z space, and then multiply the Jacobian of that transformation, and dr, d theta, and dz. Okay. So think about how this W looks like. R theta z. So first of all, if you think about r and theta, it can be as long as the coordinate xy lies inside of the boundary, it's okay, right? So r theta determines the xy coordinate of the region V. So r can be from 0 to 1, and theta can be from 0 to 2 pi. So here's the region that defines the circle area of the radius 1. How about z? So we know that z is from minus 1 over y square and 1 minus y square, sorry, 1 plus square root of 1 minus y square. So if I express y in terms of r and theta, it becomes 1 minus r square sine square theta, and z 1 plus r square sine square theta. So, well, I cannot draw that. Maybe using the MATLAB you can. But anyway, so here's, I don't know, but there's some bounding region of the range of z. Okay. So I'm going to write that out. So we have 0, 1, 0, 2 pi for r and theta. And for z, we have minus 1 minus r square sine square and 1 minus r square sine square. And we take the integration on z first, and then theta, and then r. So there's 1 here, right? So if you take the integration of 1, it's just z. So this is 0, 1, 0, 2 pi of 2 times 1 minus r squared sine square z, theta. And then d theta, dr. Oh, sorry, I forgot r here. So I have to multiply Jacobian, so we need r. Okay, so we have r, 2r. 2r. So again, I have to multiply the absolute value of r, but we always have a positive r, so I don't worry about the absolute value sign. And then it seems like I have to integrate r first, then theta. It seems easier. So I'm going to switch that order. It's okay because r and theta, the range doesn't depend on the other variables. Okay, so I can switch this to 1 over 2 pi, 1 and 2r minus r squared sine square dr d zeta, dr d zeta. So again, as I mentioned in the words, but let me write that out again. We can switch this integration because the limit do not depend on each other variables. Okay? So from 0 to 2 pi, let's say, how do I get 1 minus r squared sine zeta? So zeta is considered as constant, so we get 3 over 2 to power, and then 2 over 3, and then minus 2r sine squared zeta 2r, right? Right? From 0 to 1. So we don't have r here. And we don't have 2 here. So we get 0 to 2 pi of 2 over 3 minus 2 over 3 of sine square, and r becomes, if r is 1, then this is 0. When r is 0, I get 1 minus, sorry, so when r is 1, we get non-zero, right? No, I'm sorry. So r is 1, yes, r is 1, then I get 1 minus sine square 3 over 2. When r is 0, I get 1. So this is the result. So we have d zeta. Okay, so and then what we have is 0 to 2 pi of, let's say, let's take out this minus 2 over 3. So, and negative also. We get 2 over 3. And then what we have is 1 over sine square and 1 minus cosine cube d zeta. Right? How do you compute 1 over sine square? I forgot. How do you compute that? One minus cosine square. Well, let's think about this way. Well, first of all, we have 2 over 3 to 0 to 2 pi. And I'm going to split that cosine cube as cosine 1 minus sine square. So canceling this cosine square, sine square, I have minus cosine, is it minus minus, so it's plus, actually, plus. Sorry, so first of all, this is 3 over 2, right? This is 3 over 2. So I always have a positive sign here. So I need a positive sign. So I just don't use the cosine square, cosine cube. I need absolute value of cosine cube. Okay. So here I need absolute value here. Okay. So by taking a canceling sine square and sine square, what I have is cosine theta absolute value, and then plus sine square and 1 minus cosine theta d theta. Okay. So here's the thing. So if you think about this fraction here, this fraction, sine theta becomes 0 at 0 and pi and 2 pi, right? So it seems like this fraction doesn't make sense, or seems like it diverges at 3 points on the interval, but it doesn't, because the numerator also goes to 0. So using the L'Hopital's rule or other method, you can show that this is actually continuous. This part is not diverging any of these points in the interval, but it's continuous on this 0 to 2 pi interval. And also, let's see. Is there any easy way to compute this? Let me use the method. Int of 1 minus cosine t. I'm not going to add an absolute value sign here yet. I just want to know how to compute this. So sine t square, right? Tangent? Really? How about 1 plus cosine t minus cotangent? Okay. So on the first part it's 4, so it's 8 over 3. And then for the next part I have to divide into 3 pieces. 2 over 3. First take the 0 to pi over 2 of sine square 1 minus cosine theta, and then pi over 2 to 3 pi over 2 sine square 1 plus cosine theta, and then 2 over 3 pi over 2 to 2 pi of the same thing, d theta. Okay. So let me write that in here. So 8 over 3 plus tangent theta over 2, 2 over 3 from 0 to 2 pi plus 2 over 3 cotangent theta over 2 from pi over 2 to 3 pi over 2, and 2 over 3 tangent theta over 2 from 3 pi over 2 to 2 pi. So I think it would be easier if you just use the symmetry of this volume, but it happened here. So it's 1, right? Tangent pi over 4 is 1. And cotangent 3 pi over 4. 3 pi over 4. And cotangent pi over 4. So minus 1, minus 1. Okay. And then how about this part? So tangent pi is 0, and tangent 3 pi over 4 is negative 1, so it's positives. So they all cancels out, right? So 8 over 3. Okay. So I didn't make a mistake, right? So even though I made a mistake, just a minor mistake, it's important to know how to compute that, not exact values. All right. So what time is it? Okay, so it's almost over. So we're finished here, and we're going to talk about the integration more on the next time. So, right. So far we talked about the integration of function, real valued function, and the next time we're going to talk about the vector integration over the vector valued functions. Okay, so we're going to introduce all the notations, curl and divergence, and the meaning of those things. So if you have time, please read the textbook or the slide before the class so that you can understand better. And don't forget, the homework is due on this Friday. If you have any question, please ask any time. And see you on Friday. So Friday class is on the classroom. So thank you for listening, and bye. 시간 좀 많이 지났는데 들어주셔서 감사하고요. 질문 있으면 이제 수업 끝나니까 다른 수업 가셔도 되고, 질문 있으면은 남아서 카톡에다가 알려주세요. 고생하셨습니다. dr, d세타 적분 순서를 바꿔서는 안 되는 건가요? 분모랑은 관계없고 이게 저기 뭐야 극점이라고 하니까 그 적분 범위가 변수에 의존하면 막 바꾸면 안 돼요. 그러니까 이제 후빈이 정리해서 여기서 이제 순서를 바꾸면은 요 범위 함수가 달라질 수 있잖아요. 그래서 이제 이렇게 순서를 이거 그대로 바꾸면 안 된다고요. 그러니까 x가 A에서 B까지고 y가 G1에서 G2까지면은 그대로 이걸 그냥 바꾸면 안 된다고요. G1, G2를 뒤에 놓고 A, B를 앞에 놓고 이렇게 넣으면 안 된다고요. 그러니까 이게 새로 이 같은 범위를 정의하는 새로운 표현식을 찾아서 바꿔야 돼요. 요게 좋은 예제긴 한데 제가 직접 풀어드리지를 못해가지고 요거 한번 해보시면은 무슨 말인지 알 수 있을 거예요. 고생하셨습니다. 네, 질문. 슬라이드 13. 윗구? 슬라이드 13. 여기서. 그러니까 우리가 JT를 곱해야 되잖아요. 요 식에서. 여기서 JT를 곱해야 되는데, 이제 우리가 치환을 할 때는 EX-Y를 U로 한단 말이에요. 그러니까 정확한 치환은 X는 UV에 대한 함수, Y는 UVZW에 대한 함수, 이런 식으로 돼야 되는데, 이제 치환을 실제로 적용을 할 때는 XYZ에 대한 표현식을 어떤 간단한 문자 U 또는 V 이렇게 치환을 한단 말이에요. 그러니까 말하자면은 이 변한 T를 구하는 게 아니고 역변한 T의 함수식을 구한 거거든요. 그러니까 우리가 변한 T의 자코비안을 해야 되는데 역변환을 구했으니까 일단 역변환의 자코비안을 구한 다음에 그거에 역수를 취해 가지고 원래의 자코비안을 구하자, 그런 의미예요. 여기는 간단하니까 이제 얘를 U로 했을 때 뭐 X랑 Y를 UV에 대한 간단한 표현식으로 다시 바꿔서 1차 변환이니까 할 수도 있는데, 나중에 이제 막 제곱이 나오고 복잡해지면 그렇게 다시 바꾸는 것보다는 그냥 그대로 두고 역변환의 자코비안을 역수치해서 구하는 게 훨씬 쉽거든요. 제가 나중에 이제 좀 어려운 문제 좀 들고 올게요. 지금은 일단 개념 확실하게 하고 문제 좀 풀어보죠. 네, 고생하셨습니다.